Okay, so going back to example 1, I would suggest now that you have a go at this. Calculate the mass difference for a helium nucleus in atomic mass units and in kilograms. Now the mass difference is just the difference in mass between the mass of 2 protons and 2 neutrons when they're separated and they're individually situated, and the mass of a helium nucleus. So pause the video and have a go at that. Okay, so let me show you how to do this. Well, often we call the mass difference the mass defect, or delta M, and the way we do that is take the mass of the individual nucleons, okay, and we take away the mass of the helium nucleus, which is less than that, and you find that if you take away these two numbers, you're going to get a mass of 0.030, and that's going to be 37, isn't it? Okay, so there you go. So you can obviously just put it in your calculator if you want. It's up to you. There you go, 0.03037. So that's the mass defect in unified atomic mass units. Now if we want to get that into kilograms, we're just going to need to do 0.03037 multiplied by 1.66 times 10 to the minus 27, because remember 1U is that number in kilograms. 1U in kilograms is 1.66 times 10 to the minus 27, so this number of unified atomic mass units multiplied by that will give us the mass in kilograms. Okay, so 0.03037 multiplied by 1.66 times 10 to the minus 27 is going to give us 5.0414, okay, times 10 to the minus 29 kilograms, okay, and you could round that to 5.04 times 10 to the minus 29. Whoops, that's supposed to be a 9, not a 4. Okay, 10 to the minus 29 kilograms. All right. So that is the answer to this question. Okay. Now, one of the things I should have said earlier is this. Notice that the difference in mass between these things is absolutely tiny. It's very, very small. It's a minuscule number of kilograms, okay? Ridiculously small. Times 10 to the minus 29 kilograms difference. So it's absolutely tiny, okay? Very, very small difference in mass. So it's very difficult to detect, all right? But what you'll find is this. This is interesting now. Example 2 says calculate the energy equivalent of this mass difference. So we've said that this mass, okay, the fact that the neutrons have lost mass, so to speak, that missing mass there has been converted into energy and released, okay? So when we put these 4 neutrons together, the combined nucleus has less mass. That mass that has been lost, so to speak, is converted to energy and then released as kinetic energy, okay? Now, we know that Einstein's equation can be used to calculate how much energy that is, okay? Because essentially what Einstein's equation tells us is this, or what Einstein's equation is saying is this. What's the energy equivalent of a certain mass? It tells us the equivalence, it defines the equivalence between energy and mass. If we've got a certain number of a certain mass, how much energy does that correspond to? That's what Einstein's equation is essentially saying. Now, we've lost this much mass from our nucleus. Now, remember the mass has to be in kilograms. 5.04 times 10 to the minus 29. And we're going to multiply that by the speed of light squared, which is 3 times 10 to the 8 in a vacuum or in air squared. Now, because you're multiplying a tiny mass by this value here squared, you're actually going to get a significant amount of energy then, okay? So let's calculate that. So we've got 5.04142 multiplied by 10 to the minus 29 multiplied by 3 times 10 to the power of 8 squared, and that gives us 4.537 278 times 10 to the minus 12, and that is in joules, okay? So we can round that up to 4.54 times 10 to the minus 12 joules. you may not think that that's a huge amount of energy, and it's certainly not a huge amount of energy, but considering this is from one nucleus, from two microscopic protons and neutrons put together, that's a significant release of energy, considering those circumstances. So we've just done example 2, but let's just take a little look at that now. So what we had here was, here are our 4 individual nucleons, and this is our combined helium nucleus, okay? So these are 2 protons and 2 neutrons that are completely dissociated from one another, okay? So they're so far apart that they don't feel a strong force, and they have no interaction with one another, so to speak. And this is our helium nucleus, okay? We know that the mass of the individual neutrons is greater than the mass of the helium nucleus. So when we combine these together to make our helium nucleus, there's a decrease in the mass, okay? There's a mass decrease, a mass defect. Okay, so the mass of this is less than the mass of the individual neutrons that you put together to make this nucleus. And that mass there, that loss of mass, the mass that has been lost has actually been converted into energy, okay? 4.54 times 10 to the minus 12 joules in this case, okay? So when we put these 4 nucleons together to make the helium nucleus's mass is less than the individual nucleons, and that mass is converted into energy, which is released, okay? Now if you look at this from the other side, so to speak, here's your helium nucleus, okay? And if you want to tear this nucleus apart, break it apart, so that then we have the individual nucleons over here, okay? So this is your helium nucleus, and these are the 4 individual nucleons when you've torn it apart, okay? You've broken this nucleus apart into its 4 individual nucleons. You've pulled these nucleons out. It could be one at a time or all at once, okay? Now to do that requires energy, because the nucleus here has a lower potential energy than these individual nucleons, okay? This nucleus is in a lower energy state because these nucleons are bound together by the strong force. They're in a lower energy state. And to pull these nucleons apart, you've got to overcome the attractive strong force, and that requires some energy. And the amount of energy you would need to use to do that will be 4.54 times 10 to the minus 12 joules, okay? The opposite of this reaction, so to speak, isn't it? Now this is called the binding energy. It's a bit confusing. It's not the energy required to bind the nucleus together. That is not correct. So make sure you get that out of your head. That's a common misconception. The binding energy is the amount of energy required to dissociate the nucleons from one another, okay? So the amount of energy required to pull all of these nucleons, all 4 of these nucleons apart so that they're dissociated from one another. That's the binding energy. The binding energy is the energy required to break apart a nucleus and dissociate those nucleons from one another. Pull them apart, okay? Or it's the energy released when nucleons are combined together into a nucleus. But the usual definition is the energy that is required to break apart a nucleus, to break it up and to dissociate each of the nucleons from one another. Okay, so that's the binding energy. Now, the binding energy of this is the binding energy for helium. Different elements have different binding energies, okay? And it turns out that actually the bigger the element, the more binding energy it has, okay? Or the bigger its binding energy, I should say. So the bigger the element, the bigger its binding energy. Right, there we go.